what's our background, what other speakers may talk about. And I decided to not talk about too much about method, but mostly my opinion and experience on how I worked on the junction between machine learning and astrophysics. So I'm Case Wong. I'm a postdoc at Flatiron Institute. My day job is to someone has a problem. The case, I can't fix this. Can you do that? Yes, I can do this. That's kind of my job, usually with machine learning and related to astrophysics. But I'm going to basically tell you that today. And we're going to have a discussion after my talk. So let's go. So my background is from the gravitational wave side, and that's one big part of my science that I care. And if you don't know what gravitational wave is, they basically ripple of space-time that help us find black holes and neutron stars and stuff. And recently, the fourth observational run has started. And this is a tweet from LIGO saying, hey, this is all the amazing things that we're going to deliver. We're going to have unprecedented amounts of data, which is about 100 events, which to normal astronomer, that's like, what are you talking about? It's 100 dots. Like if I have a survey that's going to cover 100 stars, you'll laugh at it. But for LIGO, that's an achievement. So that's good. And so it's an ongoing field, gravitational wave thing, and events are coming in hot. Oh, yeah, actually 29th. Last night I checked, it was 28th. And this is live update. If I do F5, it may comes up another one. But so it started in May, and it's been, what, like 2 or 3 months? It has about like 30 events. So around 10 events per month, and that's a great deal for gravitational wave scientists. So most of the people from this conference doesn't really work on gravitational wave, but this just sounds a similar pitch. If you ever go to a conference, listen to like a big talk, it's like, our instrument's working, there's next generation things coming, a lot of data, and there's all these challenges. That's usually the pitch that we hear. And it's the same for gravitational waves. I'm just gonna draw an analogy here. And future for gravitational waves also on the horizon. There are these ground-based detector, Einstein telescope, which is a Europe-based effort, and Cosmic Explorer, which is a US-based effort, that's going to scale our detector and give us really tremendous amount of data. And we're going to shoot something into space, of course, LISA, to detect another class of event. And these next-generation detector are going to really change the landscape of the field. And I mean, most people don't work on gravitational waves, so I'm not going to go into detail of that. But I was very excited about having 100 events per year now, in 04. But in the future, a ground-based detector, the next generation ground-based detector is going to give us 10 to the 6 event. And the way that people usually say is like, if there is a binary black hole and a neutron star, whatever they are, in the universe, they merge, we'll detect them, everything in the universe. So it was pretty cool. And this is usually the spiel that people give next generation. Now you're the scientist, you're the future. Let's work on this, right? And they'll give you all the challenges. So that should sound familiar. I mean, even the gravitational wave part is not familiar. But then, of course, like given challenge, given data, then the question is, how do we solve it? And these days, it's very trendy to turn to machine learning to solve it, because that gets funding, so that's good. But also, maybe it can solve your problem, so maybe it's value added. Is there someone I can say? Oh. So I'm just going to briefly give you a sense of what are the problem that we can solve we may hope to solve in gravitational wave with machine learning. So one problem is about search. So this is a spectrogram for how the gravitational wave data channel look like, and none of these are data. These are actually glitches, but to separate glitches is the same thing as like to say where is the signal. It's kind of the same side. So people have been trying to deploy machine learning techniques like a ConvNet, like any off-the-shelf stock algorithm that you can deploy to say, if I look at this picture, can I identify the glitch? Right? Okay, sounds pretty standard. People have been doing things. That's doable. So there's search. And then there's another class of problem that people want to solve is like we use simulation a lot. And the reason why we can detect the gravitational wave, for the most part, is actually because we have very, very good model, which is GR. and give us a very good template to match filter our signal. So people want to look into how we can use machine learning to further enhance either the speed or the accuracy of this simulation. This is just like a placeholder that, a binary black hole merge gravitational wave. Okay, I'm going to cut the long animation and just, like, okay, at some point they merge. When the first event was like detected, this was played all over the place if you're old enough to watch that. So yeah, like when two black holes merge, they compute a lot of tensor under the hood to really simulate how the gravitational wave signal look under the hood. So anyway, my point here is like using machine learning in simulation is something that people also think about. And the last class of problem that I want to mention is inference, which is hold near and dear to my heart. It's like, given some data, what could be the cause behind this? And it's pretty obvious, isn't it? So it's the same thing that, given our data in our detector, what is the, let's say, the masses or the distance to the source? So that's the problem that I work on a lot. And today I'm going to use a couple examples. In inference, there's also other things in simulation and searches I can tell you more. But mostly I will focus on inference. And then I will talk about, this talk is actually more about opinion and a method. And the reason why I decided to talk about like my opinion and experience is like, I work on a pretty broad class of method, and to sell one of them to you is like doing unjust. And we have amazing other speaker that are going to talk about kick-ass method. And I'm like, okay, I'm not really expert in any of this, so why would I? But I really want to bring my experience on how to choose the method for your problem. And that's my opinion. I could be wrong, right? Like, okay, case is a little bit dumb, and it's like choose the method in a wrong way. That's fine, but I'm just going to like show you examples, like what I think is working in gravitational wave and what is not working in gravitational wave, and maybe you will find useful. And primarily, this is the two problems that I was keeping in mind. Is like, should I really use this method for this problem? Or maybe this method is not the greatest method for my particular problem. Or something that sometimes I found is like, maybe we should even rephrase the problem such that I can use the method in an optimal way that I learn the most. So hopefully that come across in the talk. Okay. So let's get into the, by the way, if there's any like clarification problem in the process, just, a case, that's wrong, that's fine.
If you're allowing interruption, can I just ask,
yes.
Is the Cagway detector functioning?
I think they're on, but that doesn't mean that they're doing a...
They might not be at full sensitivity yet.
Oh, they're far from full sensitivity.
Okay, but
yeah.
They do have an operation.
They're supposed to operating, yeah. I don't know whether it's like right now or not, but like in the last run, they already operate, but they basically do nothing.
Right.
Okay. So the first thing that I'm going to talk about is like simulation-based inference. Okay, I saw some of that in some people's slides, so that's going to be cool, and I have pretty strong opinion about that. So what is simulation-based inference? Before going to gravitational wave, these are some of the examples that is find some success in this domain, I mean, in this effort, method. So in the case of cosmology, what you can do is like, okay, we observe a lot of data, but to really compare our model to the data, usually you need to have some simulation. That is pretty expensive. You need to put gravity in, you need to put some baryon, maybe galaxy physics in. So it's quite a lot to simulate. And if you want to do some MCMC sampling, you really need some number of simulation that is usually not achievable. And so what people do is like, oh, if I first generate a large, or somewhat decent-sized bank of simulation, can I learn to represent or emulate these simulations? And then I can, that's the AI engine part, then you can plug it into your inference machine using this emulator as if it's the true simulation, and then do the inference. Same things go for particle physics, right? The detector, particle detectors are pretty complicated machine, and to go through like a full simulation to go from the jets that get released in the collision all the way to your data, it's a pretty expensive process and pretty trouble, like annoying process. So what people do is like, okay, the instrument is there. We can simulate the behavior of the instrument. So let's generate simulation, use some machine learning magic to try to emulate that. And then I can once again plug it into my inference machine just as if I have the entire model for my detector. So that's broad stroke, for the people who don't know what simulation-based inference is. Like you simulate, you train, and then you compare with data. Okay, simulation-based inference, fairly straightforward idea. And in gravitational wave, people have been trying in different contexts. So one way that we can do it is in the single gravitational wave event context. Okay, so on the left, is illustration of the data, how gravitational wave data looks like. The x-axis is time, y-axis is some representation of strain. The dark blue is the raw data. It's like garbage, like if you just look at it, you're not going to find anything. But underneath it, there's the cyan, which is the data. And your task is to, given the data, you need to tell me what is the masses of the event. Straightforward enough, you just like, that's about right. It's 30 solar mass. All the gravitational wave scientists can do that to a degree. Okay. So all the scientists are pretty well-trained machine to do simulation-based inference.
Is that typical signal to noise?
No, I mean, this is just an illustration. I mean, but like, yeah, this is a very, very illustration. But usually the typical signal to noise is, well, I mean, you can't really see the signal to noise here, but the signal is usually even smaller.
When they release those strain
Right.
plots, they've
Right.
done some filtering on
Yeah. There's low pass filter. I mean, this is already low pass. If you don't low pass it, it will actually have some structure.
I see.
But like this is whitened already, and we do some magic trick to it. Okay, so let's see if this render well. Okay, so this is the tweet. I live on Twitter. X. This is a great work from Max Stacks. Actually, I think it's in Potsdam, EI, that they, huh? Oh, so he moved. I see. Oh, I see. Okay. My bad. There's a great student that they train something called normalizing flow and couple with a couple more technique, which is shown on the top right. But basically, what they do is like you can generate the noise. Okay, we can do that. We can simulate the model very, very well. So then, since we can simulate the signal, and then they can just compare, use that to compare with real data and draw a sample from it very quickly. Okay, I'll get to why this is an important problem of gravitation and why people want to do it later. But they can do that, and it's reasonable. Okay, and this is this cool animation showing that they're saying, this is actually robust and well-tested. Okay, it works. That's the point. Good. All right, so we can do this for one event, and of course we can do this for many events. And this is something that I did in the past. I didn't make these figures. But so instead of working on a single event, we can actually ask the same question on a population level. Let's say I have a catalog of gravitational wave event, and I can simulate that. Can I try to build some emulator to understand what process drive the existence of this catalog? So this is a usual illustration of like how people model the whole binary evolution process. You start with binary main sequence, and you evolve them in this very complicated way that I don't understand, and until they merge. Okay, and then this is a somewhat fast prescription to generate a population of gravitational wave, but it's slow enough that you don't want to do this online when you compare with data. So I built an emulator. So basically, once you run this simulation, a lot of these process, then you end up with histogram, okay, a catalog, simulate a catalog. This is just to show, we have cosmic, CMC. These are different simulation. One is isolated simulation. One is in cluster, these binary star in cluster stuff. And they generate different distribution in the masses, okay? And given this distribution of masses, now you can go compare with our catalog, because now we have about 100 events. And then we can compare to that and try to understand some physics behind it. Alpha is some parameters that control some process called common envelope efficiency that is parameterized in cosmic. And RV is the typical size of the cluster parameterized in CMC, but and, f is the mixing fraction. The plot itself doesn't really matter, like if you don't work on this topic. But the idea is, again, simulation-based inference can work on a population level. And if you believe me, which you have no reason to not believe me, then we can safely conclude most of the BBAH, like binary black hole, this is a particular binary black hole inference, are from cluster. Strong statement, bold claim, and I don't believe it. So I made this paper, the full disclaimer. I made this paper, and after a while, I was like, guys, I think I don't trust my paper. That's and the question is why. One part is because I'm me, and I'm usually skeptical about my own stuff. But let's take a moment to think about it. Why, or like if you put you in my shoes, like why I would trust the first one or the previous example more so than my population model. Okay, I mean, I'm not going to go through the exercise of like asking people. I'm just going to give you the idea of what really lies between there. It sounds very similar, right? We simulate like on a single level, single event level, or on a population level, or in particle, in galaxy, they're all the same thing. You simulate, you emulate, you compare with data. It sounds pretty similar, but there's a critical difference between single event example and population. And what's the difference? Yeah. So before I tell you the difference, which is the punchline of this slide, let's think about like the perks of SBI, like simulation-based inference. It's really fast inference. We have amazing GPU, you train your emulator, it runs like instantaneously. You don't need to wait for like 2 weeks for your posterior plot to come out. So that's a good thing, right? Low retuning human effort. This is a quote that I kind of stole from Ben Wando, that he said, the good thing about implicit likelihood or simulation-based inference is you decide one day, you decided your simulation has a bug. You change the code, you press a button to make the simulation, you press another button to emulate it, and then you press another button to get your posterior. You don't need to like, it's my likelihood. You don't need to spend like a couple weeks or months to rethink whether your likelihood is correct or something. It's really low retuning human effort. When something in the simulation change, you just say, hey, go, and you get a new posterior, hopefully, if you have a big enough computer, right? So that's good. And they have really flexible assumption because the assumption here, you don't need to write down your likelihood anymore, right? You don't need to say, is this Gaussian plus the term. The only thing that it's asking here is like, can you simulate it? If you can simulate it, you can do some inference, barring a couple of things. So you can put really flexible assumption into this simulation, right? Now, there's no real free lunch in there's a no free lunch theorem. And there's some dangers coming from SBI as well. Why is my math negative? I love this part of, so imagine if I train a machine that's like the best machine in the world, and I run my inference on a single event. And then I figured that, the posterior looks fine, except it has a tiny tail that go into like negative mass. I have two options now. Like either I decided this is a bug, I need to do some more thing, or I go to ask for a Nobel Prize. I could do either. But it's obviously one is smarter than the other. So there's some dangers if you're not being careful and not really understanding what you're talking about when you use the result of SBI. The other thing is, are we really winning? So and this ties to the conclusion of this slide is that, and when I was saying, it's really low retuning human effort. You change something in the simulation, you press a button, but that has carbon footprint, right? You need to simulate, again, the whole bank, right? You can't just re-simulate one of them. Okay, you can have some techniques that let you do that, but you really need to redo your simulation a lot. If every time that you want to do a new inference, then you need to re-simulate, that doesn't really make sense, right? Because do you really win? Or you might as well just simulate, then just directly compare, is this simulation good or not? Because I can do that as well. You don't ask for continuous behavior in this target space, but you just ask, is my simulation agree with the universe? And once you have the simulation, you can ask specifically for this simulation. You can't ask for a similar one, but But that usually gives you roughly the same conclusion anyway. And finally, again, carbon footprint. I care a lot about speed, so I do care a lot about efficiency in compute. So while it's low human effort, that is compute in it. So if you can't afford that, that becomes a problem. Now, when it comes down to why the first scenario is better and the second scenario is worse, I think this is my opinion again. I could be wrong, but I think if you have a fixed model and you have changing data, do it. You can try it. There's nothing wrong. You may still run into why my massive negative problem, but it's all right. You have the same. In our case, we have the same GR model. They're going to predict the strain, and then you just change the data. I have new data coming in. OK, it's the same model. You don't need to retrain, and you just keep pressing the button. Posterior out. You're happy. But if you is actually trying to falsify what goes wrong or test your simulation, I don't think that's the greatest scenario to use simulation-based inference. Because if you think about a population case, what I want to learn about is some process related to the simulation. I have one catalog, and it's a growing catalog, but the catalog is changing every couple years, so it's not really changing that much. So if your data is actually fixed, but you want to constantly change your model, you don't really win because you need to constantly resimulate and then train and then do inference. You actually lose a lot. You might as well just simulate and compare. Is this simulation correct? Yes, good, right? So that's some success and failure of machine learning in inference in particular. I think this is working, so that's why I have echo. Now, so that's the first spiel. And from now, it's just going to be success. And the second thing that I'm going to tell you about, so that was SPI. The next thing that I'm going to talk about is hybrid method. I love hybrid method, and let me give you the reason why. Actually, how I'm doing in time. I'm doing fine. So as I said, one of the main problems that we want to solve is inferring source properties. And this is actually a non-trivial problem in gravitational because it costs us $1 million. So in the last observational run 03, there is about 100 events, okay? And we spend about 100 million CPU hours on getting the mass. Let this sink in for a second. That's just absolute insanity, right? These are just random wiggles, like sine curve. And we just trying to say, given the sine curve, what's the mass? It's like 2 numbers or 15 numbers, really. It's not that many numbers. It's not that hard, right? It's wiggles. That's always what I said. Gravitational wave is just wiggles. Why it is so hard to find the properties of the wiggle? Yes?
In your figure on the right, what's kind of the hard line?
That's just contour, like the 90% interval.
You mean this line? Yeah.
Oh, that's the definitions of M1 and M2. The primary mass has to be heavier. Yeah. So this is a $1 million problem. That's why people want to emulate and go bypass it, right? If you don't need to spend 100 million CPU hours, which translates to about $1 million, then you save your money, right? So there's the simulation-based part. But what I did is actually, this is just to tell you why gravitational wave is so hard. And one of the reasons is sometimes it can be multimodal, so that's rough if you want to do sampling. Or sometimes this is actually a posterior distribution, and it's aligned. If you zoom in enough, it's actually have some width. But the square is where your prior live. So your prior to posterior volume is huge. So that could be quite hard. And so instead of going simulation-based inference, one day I look at the problem and say, there's no chance. I mean, it's just wiggles. It has to be easy. And then we decided to build something to solve that. So instead of getting, is Patrick here? It's like the people who in JAX. Who have heard of JAX? Who love JAX? I recently tweeted on Twitter saying that I officially like JAX, so I love JAX. And I think, we don't necessarily need to go all into just the algorithm or, all this complicated network, CNN, transformer, all that. But infrastructure around AI or machine learning is actually really, really cool. And they can allow you to do amazing stuff. So JAX is one example. Half a year ago, I would have a stroke if I market JAX, but yes.
Could you please explain
Yes, this is what I'm going to do now because I love it. So JAX is a package provided by Google on it's open source package on available on GitHub that support. It basically has a very it's a code if anything that I said wrong, Patrick, please correct me. But it's a code transformation library basically that allows you to if you code with under some JAX agreed syntax, then you can take advantage of a couple of transformations that allow you to do, including automatic differentiation, just-in-time compilation, vectorization with email, and it natively run on GPU, and there's a couple more good things associated with it. And these are some of the examples. Let's look at the gradient. So on the left is how you would ask for a gradient of a function in JAX. So you need to import the library, and then you code up your function. Instead of calling NumPy, you're going to call JAX NumPy, so that the program actually knows all the primitive in the operation that you use. And then let's say you code up tangent hyperbolic. And if you want a gradient of tangent hyperbolic, I mean, we can all write that. We took calculus. But let's say you have a very complicated function that you wrote down, but still, you can get the gradient of that function with respect to its argument simply by calling grad. That way, do something under the hood to get the gradient for you. And now, grad tang is a function that you can call on whatever input, some input. And the same can happen for just-in-time compilation, okay? So you wrote this function in JAX, you call JIT, and magically become faster, okay? Or, some factorization, and it runs on GPU natively. So you don't need to change too much about it. Yes?
Is there something JAX offers that PyTorch doesn't have?
Huh, say again?
Is there something that JAX have that PyTorch doesn't have, or why are you using it?
My understanding is like JAX, so the main thing that JAX can offer is XLA, that it's infrastructure that I think it's anything wrong, please correct me, but it's a language that basically is intermediate language that compile code down to, yes? He's from Google.
Yes, so for context, where he doesn't know reply, I do a lot of Jack work internally. So to answer the question, all right, so yeah, to just briefly answer the question, I won't exert the talk for too long, is things like forward mode auto differentiation, it does much better. The compilation under the hood, again, it does much better. It's one of these things where PyTorch is really designed to do deep learning very, very well. And as long as you just want to do standard off-the-shelf deep learning, great, use it. But when you start doing more scientific problems, so you want to do like a neural network inside a linear solve, inside a nonlinear solve, inside a differential equation solve, inside another nonlinear solve, and that's not a toy example, that's what I actually do in my day job, then like that composition starts creaking in any other framework that I've tried. So I think, to be honest, that's really the big selling point, is that you can really do this composition and have it work and have it actually run really fast.
One thing that I would add on top of that is, like, from my personal experience, I usually find, like, these days now, JAX, even you compile, like Torch recently have like Torch compile. The compile speed that you gain out of Torch is actually still, I think, in general, like if you use the most standard and optimized part of Torch, like convolution, then it's probably the same. But when you try to make a scientific program, then I think JAX usually have an edge in terms of like speed. And JAX actually have pretty good sharding, which I can go into hours to talk about that.
Maybe that would make up for a good breakout session at some point if people are interested. So Patrick can talk about JAX. And then we have Chris and Frank, who can talk about Julia. And we can put them next to each other and then see what. Let them fight.
Yeah. I do both, so I'll just watch. Okay, this is our stuff, collaborator and my Tom Edward at Johns Hopkins. We basically took the gravitational wave model, our waveform model, and then we coded it up on JAX. It's differentiable now. So we have gradient, it runs on GPU, and so this is just show how fast it runs. This really doesn't mean much if you don't know the performance of gravitational waveform model. But before our package, the throughput that you can get out of like putting on like an apple-to-apple comparison is about 10 to the 3 at max. So just by putting things in Jack, making sure that like you code things correctly and putting things on GPU, 10 to the 6 likelihood. That's a whole run that usually it took. There's some catch to that. But the throughput that enabled by JAX is one of the main competitive advantage that our code have versus some other thing. So people was really excited about this. And of course, the gradient lets you do some extra stuff. Another thing that I made, yes. Yes.
In your previous thing, you're like, there's no free lunch.
Uh-huh.
And I think that's also true here.
You need to buy a GPU.
And they're expensive now. The other thing I would say is that JAX moves you to a more strictly typed coding.
Yes.
So the vectorization is amazing, but it requires that your problem truly be rectangular in a certain way.
Yeah, it doesn't necessarily have to be completely rectangular, I think. You can still be smart about how you go about. But it's some overhead. It's not like, but think about moving from C to Python or the other way around. It's a different way to think about the code. So I have a student that just like, oh, can I not just for loop in Python? It's like, buddy, no. And other thing to really leverage our waveform model, I further built something called FlowMC, and this may be interest to like some people, that it's in its core an MCMC algorithm, but it used some deep learning in it, and it has a couple of features. It has like JAX support. It has some gradient-based sampler that I'm gonna show you how it works. It has been shown to work for like exoplanet and some protein structure problems, so it's like pretty good, and it's pretty plug and play. I think I won't go into like too much detail, like how to use it and how to play it, but it's everything that I do. It's open source and fully open, so you can find it, and maybe at some point I can do a session of it. But it's something that you can use, and the idea behind FlowMC is why is normal MCMC have a stroke? So normal MCMC, let's say you have a target that it's bimodal, then MCMC is basically about bias random walk that you pick your Gaussian and you start to like randomly walk around the target. Okay, and like the green circle that you saw just there, it's Gaussian. Okay, like a local kernel that's supposed to bring you from where you're standing to a local neighborhood. Okay, so it's like walking, but you can see because the kernel that I use is local, it will have a hard time to jump to the other side. So that's a bummer. It's rough to jump across. Now, what we do is as we walk around, and actually you can initialize multiple walker to do this, and as these independent process start going around and generate sample, you start to build a normalizing flow. Normalizing flow is some technique that, think of it as a fancy KDE, okay, that lets you get a very flexible approximation of whatever target that you want to go. Okay, so as you generate sample, you build your normalizing flow as a proposal. We're not using it as it's kind of like your Gaussian that you draw from and walk around, but instead of that, now you use this green distribution as your proposal to jump. Oops. Okay, so FlowMC basically on the fly build this. So you have a couple of things that start, you build your normalizing flow, and then the green is now your target. Then you can hop back and forth. It's not perfect, but that's why we still need to use the MCMC part to adjust for the imperfectness of FlowMC. Okay, I can get into like detail and why exactly how things are coordinate, but that's the fundamental idea. Alongside with an MCMC process or multiple MCMC process, you build an adaptive target distribution on the fly with some machine learning thing that it's inject, and then it can solve the problem of multimodality and local correlation and stuff like that. Okay, so putting the tools together, this is just to show that it works. We perform this on real data, and the gray, I think it's a reference. This is an old plot that, because like there's some data conditioning, it's not exactly the same, but it's very similar here. Even in this plot in the paper, it's basically exactly the same. That our result is exactly the same of like an extremely expensive 2 weeks run. So we launch a 2 weeks long run to compare with our thing, which our thing finished in 2 minutes on GPU, and actually about 1 minute and 20 seconds is spent on compiling the code. So it's really 40 seconds. And we also test this on like simulated population, and in the community, no one dreamed of like doing 1,000 population, 1,000 event simulated population, because that's just too expensive. So really, that I'm not going to go to the next slide, but really by thinking, instead of replacing the whole thing with machine learning, which is kind of like simulation-based inference, we only replace the part. In our case, is the proposal. You learn to like combine MCMC with normalizing flow such that it behaves just like an MCMC. It has all the good properties of the MCMC, but it's more efficient. So that's why I like hybrid method. It still preserves most of the good trait that usually a traditional method has. Then if whatever people come to you and ask, how do you validate it? How do you make sure it works as well as the traditional method that people have been using, in terms of convergence and robustness. How am I doing in time? Okay, awesome. This is my last pitch of what some of the success that we've been having, and it's on model design. Okay, so I've talked about the good and bad of simulation-based inference. I talk about hybrid method and its efficient as to why I love hybrid method. And now I'm going to like show you one last one that why I think or how I think about machine learning, how I use it. So okay, I have a bunch of events now. I have, let's say, like this parameter estimation. The inference process is infinitely fast. There's no problem there. What next? So shown here is all the event. I think it's in O3, the last observational run, on the total mass and mass ratio space. And each of these circle is an event, and the posterior distribution on the event, roughly, it's a contour. Okay, so given this bunch of events, we actually want to learn something out of it, like from a population perspective, like why there's a cluster over, here, right? Why there's nothing here because of selection bias whatsoever. Okay, but as an astrophysicist, I believe this tells me something about the astrophysics process behind it, right? So okay, I need to analyze this and try to conclude something out of that. And the way that people do it, believe it or not, most of the gravitation wave people are pretty simple-minded, including me. So what we do is like, let's fit the power law, right? Or some really simple model. So now I narrow it down to like not M1, the total mass and mass ratio, but let's just focus on the primary mass, the heavier mass, the distribution of the heavier mass in our catalog. And what people have been doing is like basically they write down this very simple model. It could be a truncated power law. It could be a broken power law, so a power law with two slopes and with some truncation. Power laws plus a peak, power law plus a Gaussian basically, and power law plus two Gaussian. So people just keep writing down this analytical model and trying to say, okay, given the catalog, given our model, is that correct? Like, does my model describe the catalog well? And this is what people have been getting. Like this I fetched from one of the LIGO paper. So that's been okay. We learned something. We learned that at some point, there seems to be a gap of like black hole mass. It cannot be too heavy, and it cannot be too small. It's not zero here, just to be clear. It has a lower truncation and upper truncation. There may be some pileup. Okay, so people learned something out of this. The problem with this is last run, or maybe O2. It's gonna be harder and harder because we have more and more data, so we can resolve the feature in these distribution better than better. So it's very difficult to come up with like, well, I mean, from hindsight, it's getting harder and harder to build these more complicated analytical model. And also, it's pretty hard to generalize these into like higher dimension because like, okay, in 1D, I write down a power law. In 2D, some covariance. Like if I go to 15, what do? It's a little bit hard. And this is powered by smart people, and this is the part that I think is problematic because like we don't have that many smart people. It's like someone comes in, it's like, this form is the best, right? But that guy look at the data, have fun with it, get some paper, and later on went to industry. Damn, we can't do the science again, right? So that's problematic. And people have been trying to come up with like more and more sophisticated model, like a power law plus a peak plus a spline on top, and now become a problem. It's like, why are you doing this? A spline? So population analysis is actually getting more and more challenging in gravitational wave. And what we propose is like, if you want to put a spline in, I might as well put in some just really flexible model. At that point, I don't care about whether it's a simple power law or something. So one of the work that I did with my student, I love normalizing flow by now. You should be able to tell by now. That is, we basically parameterize our population model with neural network, or like with a normalizing flow model. So on the left, it's just to show this is how the event, this is showing your event in the primary mass space. But then on the right, now we get the same thing that you see in the previous slide, like with the power law and all that. But now the model that we use is a normalizing flow. Again, some neural network. And then you can fit the data and still get some confidence interval out of them. Okay? So this is just replacing the model that we've been using, the simplistic phenomenological model, with a much more flexible model, a neural network. Okay? But that comes with a problem. I cannot point at the weights of the neural network and say, this weight means this. I can do that with a power law. I can point at the spectral index and say, the spectral index is -2. This means that. I cannot do that to a neural network, not very easily. So what we do is we use some techniques called symbolic regression. So this is a movie that made by one of my friends, Miles Kramers, and he has this awesome package called Pizer on GitHub. It's cool. Check it out. Basically, it's a genetic algorithm that mutate an equation to trying to fit the data. So what it will get, like I'm just going to tell you the I/O. The input is like you shove it data, and the output is an equation. Okay? And it has a couple of trade-off properties. So we combine our normalizing flow model and symbolic regression. So in-go the data, we fit it with normalizing flow that we have the previous slide. And once we reach a good fit of the model with a normalizing flow, then we're trying to distill the underlying model using symbolic regression. So we get an equation that is hopefully much more lower dimension that I can point to and try to explain. And in one of the paper, we basically closed the loop of like, give me data, I fit the population with normalizing flow. Then, at the end of the day, we learned that, there's probably 2 peaks and a continuum, okay? And the good thing about this is, if it works, then it's fully automatic, right? New data comes in, press the button, go, you get a new equation. And the amazing thing is, once you get an equation, it's as good as some genius comes in and proposes a form. It's just as valid, right? Like silicon computer and carbon-based computer, same thing, right? So that's why I like to use machine learning as a proposal and as a flexible model to really understand our data. So okay, so that's some whirlwind and case study of what we've been doing in gravitational wave, and I think I'm pretty good on time. And these are a couple takeaway, kind of rephrasing what I talk about in the slide. So first thing is ask what you lose. Usually there's no free lunch. Sometimes you ask your cool mathematician friend, and they come in with these awesome techniques that give you a lot of leverage. But more often than not, you lose something on the way of gaining something. So in the case of simulation-based inference, we need to, more often than not, we trade off efficiency with some robustness. And we, especially for astrophysicists, that things live far apart, that we cannot just go there and take the black hole back. We need to really ask, is that a good trade-off? Should I trade my robustness away? The second thing is you don't really need to reinvent a wheel. Science has been doing great in modeling, simulating, analyzing. Some part of the traditional method works really, really well. You don't need to replace that part. Replace the part that, some people comes in, fit a line, and it's like from the 70s or something. Replace that part with machine learning. You don't have to replace the entire thing. And in the end, machine learning has a lot of good infrastructure that helps you automate stuff and make things scalable. So think about how to use that as well, which is probably what we're going to do, at least for this week, if not for the longer period of your career. I'm speaking mostly to the junior. I'm not trying to lecture old people, just to be clear. Okay, discussion. Any question? This is like the bulk of the talk. I think I still have some more minutes to go about the discussion, right? Yeah. Okay, good. I'm perfectly on time, actually. So any question related to, yes?
Yeah, curiosity regarding the symbolic regression. How would space be dimensional?
Good question. So the reason why we combine it with so we will be thinking, okay, if symbolic regression work, why don't I just show it data and symbolic regression? Why do I need to have a normalizing flow in between? It's because, scalability, like once you go beyond like 10 dimensions, well, even there's just 4 dimensions, symbolic regression has really like, starting to have a stroke to just fit the raw data. So what we tend to do is like, just fit it with a flexible model first, capture the data, and then trying to sparsify that as much as possible, then do symbolic regression. Does that make sense? Yeah.
Yeah, so I wanted to ask about your hybrid method. So just trying to understand how you train the normalizing flow, and specifically I was wondering whether you can use the quality of the proposal in order to train the normalizing flow.
Say again?
Whether you can, so you use the normalizing flow to give you give you proposals in your Markov chain method,
right? And
whether you could somehow directly use the proposal quality to train the normalizing flow.
Yes, but I think so. The first question is, how do I train my normalizing flow? So if you have one chain, you can still do it. But like usually the picture that I give is, if you have multiple chain, let's say you start in both of the mode, independent chain will have problem communicating. Well, you can build some method that let them talk to each other. But let's say you don't use that, and you have 2 chain walking in individual mode, and they start generating sample. And on the fly, once they generate some sample, then you start to train a normalizing based on that sample. And then you create a proposal that is not perfect. And then you try to jump it, but you metropolitan adjust using the sample that generate from the normalizing flow. And you repeat the process. So you basically your normalizing flow, as you sample, it will get better and better and closer to your target. The other question is with respect to whether we can use the acceptance criteria to train the normalizing flow. We tried that with, I think it's the 4KL laws. It's very prone to mode collapse. So it's very easy to suddenly, just lose the other side, and you lose the benefit of like having multi-mode and all that. That's like an empirical thing that we find. So we tend to not do that, but it's in principle doable. Cool. Does that answer your question? I think someone's in the back trying to ask a question.
Is this thing on? I just wanted to ask you if you've thought about, so the way we usually think about emulation is you have a simulation that, say, simulates the state of the universe.
Yes.
And you want to build a machine learning method that makes a replacement or swap-in replacement for that simulation.
Right.
At the end, for many problems, like when you're trying to do your black hole measurement, you actually only care about the likelihood function. You don't really care about the full waveform. You don't need to emulate the full waveform in some sense. You only need to emulate the likelihood call in principle. And in some sense, that's what FlowMC is doing. So in some sense, FlowMC is an emulator, right? It's just emulating exactly one number, which is like your posterior probability.
I mean, it will give you a proposal, but I mean, it gives you a function that lets you a problem. But I wouldn't say FlowMC is an emulator because a part of it is still like traditional MCMC. So it's not fully emulator, right?
But the normalizing flow under the hood is trying to somehow emulate the posterior PDF.
Yeah, I mean, you're trying to.
Which is the thing you get from a simulation comparing to the data.
Fair, yeah. Like, I mean, that's true.
So it relates to, I mean, I'm not asking a question really, but I just want to make the point that if we want to make really safe emulators, it's really valuable. This is something Morgan and I talk about all the time. It's really valuable to emulate a low-dimensional thing as opposed to a high-dimensional thing.
Yes, if you fully trust the output of your emulator. The thing is, in our thing, we don't fully trust our emulator. We have metropolitan adjusted. So that we bypass. But fair point.
But it's an example. That's an example of kind of verifiable
emulator. Yeah. Fair point. Yes, someone in the back was having a problem. Yeah, for a long time. For others, if you have a question, meanwhile, scan the QR code. I think there's like a 50 people limit. I think, not everyone is gonna like scan it anyway. So there's like a tiny survey that we're gonna like look at them, discuss them interactively. Yes?
Yes, thank you for the really nice talk. I have a rather naive question about simulation-based inference. So, if you have, let's say, some kind of a highly informative prior on one of your parameters for a particular event, let's say, then would you have to retrain your model again, or is it like if you want to incorporate that prior, or yeah, how would that work?
On the single event level or on population
On a
level?
single event level, let's say.
What do you mean? Like, trying to understand what you ask. So let's say I have 15 parameters in my problem, and I have data. And if you say, if I have, I mean, by the way, I didn't do that, like Max did that. But like, you're saying if I somehow know the prior of one of the parameters very well, do I need to retrain? I don't want to speak on behalf of it. I think you should be able to just marginalize, like let's say you do the full posterior and you find the thing, but now you want to put a prior, you should be able to do some important sampling to reways to, yeah, you should be able to do that.
Thank you.
Yeah.
Yeah. So I had a question about kind of your first conclusion point. So often you're kind of describing this trade-off because we know something, we have a model for it, and we want to make it faster.
Right.
And in other fields, for example, biology, large language models, we have something that's so complex that we cannot even describe it or solve it ourselves. Where this trade-off doesn't apply because we're solving a problem that's so complex that we couldn't solve it before with computational methods, whilst we often can. Do you see potential things that we can identify where we could only have the benefit of solving a very complex problem with machine learning without the downside of losing this accuracy because we didn't have a solution in the first place?
I mean, like that sounds, this sounds more sociological problem. Than it's like if you have never tried to solve the problem before, then like the first time you solve it, you already gain. Like there's nothing to lose, right? But I think once you get there, then there must be some trade-off that you can think about. Like people now are thinking about trading off safety with accuracy or something, right? Like they're trying to instruction tune GPT-4 or something to make it more safe. But somehow people were starting, like some people complain about whether GPT-4 get dumber over time and something. I think you're right that if we don't know the trade-off, then I guess there's nothing that you can do. But once you reach the point that something starts working, then the trade-off immediately becomes like, oh, you tune this hyperparameter, so, oh, it doesn't work, then you tune the other way. So yeah, that's that.
Thank you.
Yes.
Thanks. In your symbolic regression that you did, isn't that just a modern way of what the experts were doing like 20 or 30 years ago?
Exactly, yes.
Because, well, they just had 3 or 4 functions because they couldn't handle anymore.
Yeah.
Now you're using everything that the computer can have as a symbolic thing.
Yes.
Wouldn't it be smarter to use only those for which you somehow have a guess that would come in such a model? So I think, for example, harmonic analysis, which means sine, cosine, would make much more sense than using some, I don't know, log function or whatever that would never show up. So I think a combination between a smart approach and then doing AI would probably be even more valuable.
We do that. So you can define your sets of operators. Like when you combine the operators, you can say, okay, this is Gaussian and all that. You can do that. And I think you're exactly right. This is exactly like what people like. But the point is, we don't have infinite stream of like smart people, and this is like a good way to say, just go, right? So yeah, you're totally right, and we're doing that. Awesome.
But it doesn't have the problem of dimensions, does it?
No, I mean, so the symbolic regression has the problem with like high dimensionality, and the way that we go about it is to use the flexible model. I think there may help the the dimensionality problem a little bit, because if I just show you a table, a human would first make a plot, and then go do the symbolic regression in their brain, right? So this is like just automated to do it, and like human can intervene at any point. It's like I can intervene after the normalizing flow. Is the normalizing flow reasonable? Is the plot, right? So that's why I like the approach. It's fully integratable. It's not a black box. You can unfold it like in different parts and just inspect it, just like any part of human.
And you can adapt the function library, right?
Yeah,
that's exactly the point.
That's the operator set, yeah. Cool.
More questions?
Yes.
Yeah.
How do you deal with out-of-distribution data?
Which one? Which problem are you talking about?
In general, normalizing flows seem to be have problems with out-of-distribution data when you have maybe some outliers that might be actual data and not just glitches.
I think that itself it's like a meta question. It's like at which point you care about. Well, I mean, this is a good question. So I think, for example, in some cases it could critically matter, and in some cases it's like whatever. So for example, like in this one, the normalizing flow is trained to approximate the proposal. You can have out of distribution, and precisely if you look at the tail of the blue, that's out of distribution to the normalizing flow, right? Because like the normalizing flow is not encapsulating that. But that's why we need to still keep part of the MCMC to try to go to the tail. And this is something that we're trying to show in a more mathematical way that, we're working on a tuning paper to show in how to trade off MCMC between N and the normalizing flow part to deal with that. So in this case, we're trying to use some MCMC to amortize this problem, to alleviate it. And if you think about the population problem, or this slide, right? Fixed data changing model. This is out of distribution. Your model space is now out of distribution. What if your model is not correct? And then you need to retrain your entire normalizing flow and validate again. So this critically, harm you here. Whereas in the other case, okay, we're using it as a proposal, we can adjust it, so it doesn't harm you as much. So it really comes down to how you use the normalizing flow, I guess, in the end of the day. And I guess flow MC is one example of how you can handle it. It's just like, on the way, you adjust it, you only use it as a proposal. Does that make sense? Okay, cool. Thanks. Awesome. Is there any other question before we go into like the discussion? Let's see if this works. I never tried this, just to be clear. Yeah, it works. Okay, good. So people did answer the question, and I was very happy. So what I just want to, so there's a couple questions that if people fill in the survey, you may have seen. I'm very curious, like what's going on. So this is also like a matter. This is the first talk, right? We're gonna like start the conference somewhere. So this is the distribution of like what people are bringing, and a lot of people are bringing data, and this is amazing. Actually, I was reading this slide, and people really have a lot of data, and there's some number of people like almost equal amount of people bringing method, and it's very important to, of course, I'm saying something that like sounds obvious. Oh, yeah, it's important to let them talk to each other. But how? I think like this is a very good distribution between, it's pretty even between method and data. With usually, people who build method will tend to have one method that works for all problems, and data people is like, I don't know, I have this problem. So this is great to see. What is other? Who votes for others? Come on. Who voted for others? All right, good. Like, you want to say what others mean?
Also equations, maybe, and some like problems.
Oh, sorry. Actually, would you mind like just say your name and where you're from, like just so everyone can know you a little bit? Yeah, just introduce yourself.
Okay, my name is Laura, and I think that I also bring data, but also some problems with the data. So I just pick others because it's more just that the data is
awesome.
Problems, bugs.
Cool. Any others that is like different? Of course, everyone's silent. Yeah, so very good distribution. Very excited to see what's come out of this. Next is what bugs you. So a lot of people, as Laura said, problems, right? What are the problems? And it's slow. Like now we're cooking. I love this because like all my thing, it's about making things go fast. It's wrong. I'm curious whether people think who said is wrong. You guys show of hand. 8 people. I should count 8 hands. Okay, there's David. Yeah, there's who else voted is wrong? Which is interesting. It's a very, very shy distribution, huh? I'm curious whether, like, okay, it's wrong, but is machine learning the way to fix it? Maybe. Huh?
What is it?
What bugs you? Like, usually look at problem or something. What bugs you? The thing that bugs you. It could be a problem that bugs you. An algorithm doesn't work. An algorithm is slow, or like the data. You can say the data is wrong, right? Someone didn't do a good job collecting the data, or they messed some things up. That could happen. I don't know. Interesting to get the third answer, right? Don't even know where to start. I didn't expect, that high number, but it's the same number of it's slow. So maybe it will be interesting to see whether machine learning can help. Maybe, like, I don't know, go ask ChatGPT. Exhausting. Now it comes down to, I think, who voted exhausting? Who's already tired? Yes, good. Cool. And want to say a little bit why? What part of it is exhausting?
Well, I work on modeling and machine learning, and I'm doing a lot of it myself. So I'm doing a lot of jobs. So it's kind of exhausting to have to both know the modeling in and out, make sure your data is correct so it's not wrong. Then it becomes slow. Then I wait for weeks, and then I can finally fit my model, which again takes months. So like the whole cycle takes a lot of time, which is why I'm exhausted.
Yeah. So maybe automation can solve a little bit. So it would be cool. Any others want to say a little bit about others? Come on. Yes.
Hi, I'm Linus, and it bugs me that I don't know how to figure out if I used the right kind of model, and then how to find out what the model is actually doing.
I see. Oh, that's an interesting point. You don't know what the model is doing.
Yeah,
Are you?
explain AI.
I see. Is it like more machine learning model or just?
Yeah, machine learning.
I see. Cool. That could be something to touch on. Explainable AI. Hopefully, someone take the charge.
If you're interested in that, I will do the project presentation on that.
Cool. Awesome. So these are the trouble. The reason why I want people to show hands, like see who's around you, then you can say, hey, it bugs you too. It'll be great, right? Awesome. Next things, let's see who says something. Word cloud. I didn't know it's word cloud. So what can ML is like? Speed. I love speed. What are the interesting things here? It's like, complex model. Some people like emulator nuisance. Yeah, good. Bypass missing data. That's pretty interesting. Is anyone spot anything? In marketing. Ooh, ML can help marketing. We're talking about money now. Good. Use more in spec, MCMC. Cool. So this plot is probably quite interesting. Like maybe later on I can send Tobias this. Will be.
Yeah, I guess we could put that somewhere.
Yeah,
public.
Good to keep it. Multimodality.
Is somebody filling out the form right now? Because it'd be interesting to know if that updates in real time.
I think so.
Updating in real time.
You saw the bar going up and down in the previous slide, right?
Yeah, exactly. So somebody needs to put in like not overfitting and see if it jumps. Nice.
Nice.
It's a dynamic word.
Yeah. This is my favorite tag. I think this is the last question. So is your problem really suitable for ML? So a lot of people like bring problem data and all that, and some people bring method. And this is a machine learning conference, and it was like, maybe the first question that we should ask is whether we actually need to use machine learning. Maybe not. What about that take away our job? Well, that's a problem, right? So maybe. So think about that, and most people think that it's quite neat machine learning. Is it only machine learning? Could be. It would be interesting. Swimming in data. I kind of curious. I'm gonna keep track of that whenever I talk to people. It's like, do you think you swim in data? And let me convince you that you're not swimming in data, especially when it comes to simulation. But it could be. We do live in an age that we're swimming in data. Traditional method is trash. If I was, the person, I would just shift it all the way to 5. But maybe doing a good job. And actually, this shows that maybe traditional methods is doing okay. And it's the same thing that go for the last one. All right, this is the most important question. Only 29 people. I think there's a correct answer to this. Oh.
It's funerary.
Yeah, it's the correct answer is yes. So only 29 people is ready to have fun. Hopefully this goes up as a function of time. But yeah, that's about it. And thanks everyone for listening, and hope you enjoy the conference.
Yeah, thank you for this great opening talk. Lunchtime, I would say. I'm pretty hungry. I'm starved. I didn't have breakfast. I was nervous.
Oh, thanks. Oh, yeah.
Way more quantitative use of Mentimeter than I did.
It's also like this is like review.js, so I can update like everything here, like in the slide.
I actually had to put like the links to the different because for me it didn't work. The Mentimeter didn't work. You only saw the first slide.
Yeah, like these are all like update real time. So. Oops. My bad.
If somebody wants to leave his or her bag in the lecture hall, I can lock the lecture hall once everybody left.
No, I need to find lunch.